So good afternoon, welcome all. It is a pleasure to have today Professor Jean-Marc Deshouillers as our speaker in Colloquio De Giorgi. He is emeritus professor at the Institut Polytechnique of the University of Bordeaux. Let me start with this. Actually, if I have understood correctly, he graduated at the École Polytechnique of Paris in engineer. And let me remark that it is not so uncommon for mathematicians to come from this kind of university experience. I may recall Bernard Work, for instance, but there are many others. So I had the fortune of meeting Professor Deshouillers long ago. He worked, he's a distinguished expert, mainly working in analytic number theory from several viewpoints. Let me just recall a few important results that he had. One is particularly relevant, obtained in 1982, I believe, collaboration with Henryk Iwaniec. They obtained a remarkable estimate for Klosterman sums, which are kind of ubiquitous in analytic number theory and not only analytic number theory. And there was an interplay also important with modular forms, estimates for coefficients and trace formulas, which constitute some of the deepest applications, sources of applications for analytic number theory, and are important in themselves. And that was somewhat pioneering work in this direction. Today, this is still very active field. And this work had applications to analytic number theory and modular forms. And sieve methods also were involved, so quite a wide breadth of issues. And another very relevant contribution was the complete solution of the well-known, very well-known Waring's problem for fourth powers. As you probably all know, a Waring problem is related to the problem of expressing integers, positive integers, as sums of a fixed number of perfect kth powers. And one, of course, may vary k. For instance, for k equal 2, we have the theorem of Lagrange that every positive integer is the sum of 4 squares. And there are assertions for all k. And of course, to obtain, one would like to have the minimal number of summands, of possible number of summands. And here there is big literature around this kind of issue, started with Hilbert and then continued, particularly with Hardy and Littlewood, who introduced the circle method, and so on. For fourth powers, the answer as to the minimal number remained open for a long time and then was completely solved by Jean-Marc Deshouillers in collaboration with Dress and Balasubramanian in a series of papers, actually. And I would like to recall that some of these papers are published in the Annali of Scuola Normale. And then there are other contributions, like to the Goldbach-Ternary problem, which is, again, additive number theoretical problem of expressing a number as a sum of 3 primes. I will not enter into technical detail, and just recall that he also worked in probabilistic number theory, so involving methods whose inspiration comes is shared with probability theory in part. Okay, today he will speak to us arithmetic properties of certain sequences of polynomial growth, and this also will contain some viewpoint concerning randomness, if I understood correctly. So thank you. And
okay, so thank you very much, Umberto, for this kind introduction. I, of course, would like to thank Professor Andrea Malchiodi for the invitation here. And I would like also to thank the staff of the Centro De Giorgi for providing excellent conditions for living for my stay here. And so my first visit to Scuola Normale was in 87, up to 1 year. My memory is not that that good. It was at the invitation of Professor Visentini. Okay, so well, let us go now to the topic of the day. So what we are going to deal with is sequences of integers. So integers, I guess we know what it means. For me, integers is just a non-negative integers, rational integers. 0, 1, 2, and so on. Okay, so and so this is a sequence, and to say polynomial growth, it will mean something like log un. I don't know. This is it? Okay, log un divided by log n, and you assume that this tends to a certain positive limit. Okay, so this is what I mean by C is maybe in some way the degree of un, but it can be a real number. It need not be an integer. So, for example, if you take, of course, polynomial, which are positive from some point onward, then they satisfy this condition. Okay, so this is what we call polynomial growth. I must say that I didn't notice that because I am not using the correct name. And I strongly apologize because I should have chosen something different, because the so famous sequence introduced by Leonardo Pisano is not in this category. So I hope you will forgive me. Okay, so let me give first some introduction. I want to check how this goes. Yeah, okay. They are moving one with the other. Okay. So, okay, so archetypical, how you say, archetypical example, and essentially this is what we are going to use of such functions. It's just what you take is some polynomial of degree c, which is n to the c, and n to the c, of course, is not an integer. We're looking at that, this sequence for n, which is an integer. So this is not integral, except if c is an integer. It's not integral, but to make it integral, you just take the integral part. Okay, integral part of a non-negative number, of a positive number, you just write it in decimal and you drop everything which is after the decimal point. Don't do that for negative integers, but we are just looking at positive integers, so it's fine. Okay, so this is this. And the first consideration, this was introduced in 1933 by Segal, who indeed studied Waring's problem. By the way, it was introduced exactly with this notation. The C was already in the first instance, and it's been kept forever. You see, this is the kind of notation at sigma plus IT, and you are not going to change it even if you think it's not very consistent notation. So Segal showed indeed that every sufficiently large integer, every integer can be, because if you take n is equal to 0, then you get the value 0 here. So every positive integer can be written in the form n to the c and 1 to the c plus blah, 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 plus a certain number and g of c to the c. So there exists a number g of c, which is fixed, independent of capital N. This is the Waring's problem for this. And this is when those sequences have been introduced. Okay, what is, so I think this is the only thing I'm going to say about this additive question. More interesting and better known is the multiplicative side. In 1953, PIatetski-Shapiro looked at prime numbers in this sequence. You see, in some way, what you would think is that, and this is what we are going to play with, is that in this sequence, you are killing in some way the arithmetics. You have the feeling that this sequence have no arithmetic property. And this is what we want to discuss a bit and to see whether there are really random sequences, up to which point, when they are not, something like that. If it is positive, what you would expect is that the number of n up to x, for which n to the c is prime, is something that will go to infinity, and that those prime numbers are distributed in those sequences, or they are distributed in all numbers. So you see, just to figure out how it is for all the integers, if you write, as usual, pi of x to be the number of primes up to x, p denotes a prime number. You are just counting the number of prime to the x. It has been conjectured at the turn of the 19th century by Gauss and Legendre that this should be about x over log x. That is to say that the probability, the heuristic probability that an integer around x is a prime is something like 1 over log x. So there are many primes indeed here. So what you would expect, and this was proved at the end of the 19th century, independently by Hadamard and de la Vallée-Poussin, Belgian de la Vallée-Poussin. And so this is now a theorem. And what you would conjecture is the following, that if you take the number of prime of n up to x, so that n to the c is prime, what you would expect is that the primes are well distributed in this sequence. You have killed the arithmetic in some way, so it is a random sequence. And what you would expect here is that this is equivalent. So you have x term, it's fine. And those terms are something which are of the size x to the c. So the probability that they are prime is something which is log of x to the c. And so you would expect that this is divided by c log x. Okay? So this is a conjecture for any c which is not an integer, you should have this. Okay? And what PIatetski-Shapiro proved is that this conjecture is okay for some c, all c up to 12 over 11. It's not very large, but it's something. It was in some ways we got some sort of natural sequence. At that time, it was the sequence which was increasing the maximum, which contained, for which you can prove that they contain prime numbers. It's not that easy to prove that a sequence contains primes. Okay? And I don't know, I don't think I will have much time to say something about the proof, but I will say a few words in the document I will give you at the end of that. So okay, so this was proven. Now we can do a bit better. And Riva and Sargos, I think, get to something which is 1.6. This is essentially 1.1. And what they got is something which is now 1.16. So it's very difficult to go further. And then you have something which is in some way, if you put it random, this is the advantage. The advantage of having a real parameter, that first you can say, okay, we don't know, for example, whether if you take a polynomial of degree 2, n squared plus 1, we expect that there are infinitely many primes. We don't know how to prove it. Excuse me. Yeah. And so you have some continuous parameter which permits you to measure how good you are or how poor we are, as you wish. And also, it permits you to say something. If you look for almost all C, then for almost all C, we can prove that we don't prove that this is true, this conjecture is true, but at least that there are infinitely many primes and that the number of primes is larger than this up to a certain constant. Okay, this was for the history. Let us go to something simpler. I think I have to. That is to say, just to study distribution of prime of the number n to the c in arithmetic progression. Distribution of NC. By the way, this sequence is called either PIatetski-Shapiro sequence because he has done this, or in some cases, Segal PIatetski-Shapiro sequence, referring also to Segal who introduced that. So the distribution of PIatetski-Shapiro sequences in arithmetic progression. Okay. Okay, so if you think of squares, for example, that c is equal to 2, if you think of squares, then if you look at the distribution, if you take an even number, its square is even. If it is odd, its square is odd. And so you have about the same number of squares which are even and the same number which are odd. If you count up to x, you have x over 2 plus an error term which is bounded. Okay, so you have a good distribution. But if you take modulo 3, that is to say, you look at the residue after you divide by 3, what remains, situation is not the same. Because if you take something which is an n which is divisible by 3, then of course n squared will be divisible by 3. But if you take n which has a residue which is 1, then n squared will have a residue which is 1 mod 3. But if you take minus 1, the residue will be also 1. So you have no integer which is a square and which is congruent to 2 mod 3. So you don't have a good distribution because of arithmetic. Now, what you expect in those sequences, so from now on, definitely, if I don't say anything, C always belong to 0, infinity, minus n. I'm not here looking at the usual powers. Usual powers will have arithmetic properties, and we don't want them. Okay, so 2, 1, we look at the distribution in the first step. So what we are looking at is the following. Let us say I will just write the proposition. The following, so C is between, I mean, even I want it to be increasing, I will put 1. You can also do something when C is smaller than 1, but then it is something like the square root function, and you see all the integers occur, and it's in somewhat much easier to do it when C is between 0 and 1, because you can follow what it is. So proposition, so let C be such a number, and you consider 2 integers, A, which is 0, and Q are integers. So Q will be the modulus, and A will be a residue. And what we are looking at is we are looking at the number of n up to x, such that n to the c is congruent to A modulo Q. And this is what we want to have some idea about that. And this I will denote by NC of XQA. I count the number of elements in my sequence, the first X element, which are congruent to A mod Q. And if the things are well distributed, you would expect that the number of such terms is just X over Q. It turns out that this is true. This is equivalent to X over Q, or you write it 1 plus little o of 1 as you like, X over Q. Yep. So I'm not going to give much proof, of course, in this talk, but I would like just to outline the proof, because it gives you some hint of what can be done also. And so I would like to do something about that. Now, No, I just look. The easiest thing is to know how they are distributed in arithmetic progression. Because prime is something different. In some way, what you would expect is that if a set of numbers is well distributed in arithmetic progression, then it would contain the number of primes you need. This is almost true, but there is a counterexample. If you take the number which has an even number of primes, then they are well distributed in all arithmetic progression, and there are not many primes in it. So this is the difficulty to go from one side to the other. And PIatetski-Shapiro was doing something different. He was not looking in the sequence of PIatetski-Shapiro number whether there are primes. He was looking in the set of primes. Can you find elements which are in the PIatetski-Shapiro sequence? And if you start with prime, it is much easier, you see, to say you are in a sequence which is n to the c. This is the way it does it. So, sorry? Yes. Yes, we have some bounds. It is exactly the same kind of thing that what you have in for a Waring's problem. That is to say, it depends if you want really to represent all of them, if you want to have all the representation, or so you have something which is essentially C log C. Okay. So hint of the proof. Oh. So maybe I should have started here. It's fine. What it is when you say that T is congruent to A mod Q, then it means that there exists some K integer such that T is between KQ, no, KQ plus A plus 1 and KQ plus A. You see, if you take the integral part then will be just KQ plus A. And so it is congruent to A mod Q. Okay. And another way to see that is to say that there exists K in Q in Z such that Q KQ, K plus A over Q is less than T over Q is less than K plus A plus 1 over Q. I just divide by Q. This is not a big deal. So you can see it also if you wish to say that the fractional part of T over Q is between a over q and a plus 1 over q. But I would rather introduce the indicator function of this interval. That is to say that here you have 0, here you have 1, and here you have a over q, and here you have a plus 1 over q. Of course, a can be equal to 0, and a plus 1 can be equal to q. And you put this function like that. This is 0 here, this is 1 here, and this is 0 here. So this will be the function KAQ, the indicator function of this interval, and you make it periodic with period 1. Okay, periodic with period 1. With period 1. And so what you are saying here is simply that you are saying that chi AQ of t is equal to 1. We're just saying that you are in this spot, okay, mod 1. Good. So you are interested in NC of x QA, and this you can write now as being the summation when n is up to x of chi AQ of n to the c over q. This will be exactly 1 if n to the c is congruent to a mod q. You have this characterization, and otherwise it is 0, and this is the value of the function kq. So you have a function which is periodic with period 1. It's not a bad function, so you expand it into Fourier series. So I don't know whether I need that really. Okay, I think you understand what is the KAQ, and I expand it. Oh yes, yes, of course. The integral part is not only I can remove, but it's much better to remove it. Yes, thank you very much. Of course. Yeah. You see, if you want to say that integral part of t is congruent to a mod q, this is exactly to say that the function key at the point t is, thank you very much. So then you expand it into Fourier series, and this will be the summation h belong to z of chi AQ, the h, and exponential of 2 pi I h and c over q. Okay, so this function is not too bad, but it's not exactly continuous. So these chi are not excellent, but they are almost good, because you see, when you integrate to know what is the value, you have something which is like that, and if you have some h you integrate, then you have something which will be 1 over h. Okay, because you have complete set, except maybe for one little remainder, and so you have something which is 1 over h, because we have the size of it. Now, if you're really a beginner in mathematics, real beginner, you see that you think that the harmonic series converges. If you're a bit more used with mathematics, you say that it doesn't converge, and the privilege of being very old, if you are very old, you know that it converges. And so don't worry too much about the convergence of that. It's almost good. So in any case, this converges in the good sense you are used to, and this is a finite sum, and so you can exchange the sums. So you exchange the sum, and you say this is the sum when h belongs to z of chi AQ of h, the Fourier coefficient, and then you have the sum n up to x of this exponential term, exponential 2 pi I h and c over Q. Now, if you think of that, there is one term which is easy to compute, is the term when h is equal to 0. If h is equal to 0, this characteristic, the value of the Fourier coefficient, is just the integral of the function on the set 1. This is a over q, this is a plus 1 over q, and so the integral is 1 over q. So the Fourier coefficient is 1 over q at the point 0, and this sum is just trivial, because since h is equal to 0, this exponential term is just equal to 1, and you're just counting the number of elements, which is x. Okay? So what you have is something which is x over q plus, and then when you have h is different from 0. Okay? Now you think, if you think of squares, what you will get is that this is periodic, this function, and so what you will get is just some, on a period, you have a Gaussian sum, and these Gaussian sum are not always 0. You don't have always compensation. It's what we were saying for squares mod 3. Gaussian sum is not 0. But here, what you can expect is that you have indeed cancellation in all those terms when c is not an integer. So now all that is essentially introduced. It was by Hermann Weyl in 1916. About study about distribution mod 1 is exactly this. And for this type of function, it was studied by van der Corput, essentially, let us say, in 1922. So this is very basic things we have, okay? And so now you understand what happens. If you can say that you have cancellation in those sums because c is not an integer, and van der Corput tells you that you can do that, then essentially what you have is that nx of qa will be x over q plus an error term. Okay? I don't go further into that, but this will be enough for the proof, and you have everything you need. So there are two consequences of this. Two consequences. First, now you can work out what is, you know that in this sequence, I said there is cancellation, but you can measure what are those cancellation. And essentially, those cancellation will be something which is polynomial. That is to say, this sum, you will have a bound for the modulus, which is x to something 1 minus a delta. Okay, this delta will depend on h, will depend on c, will depend on q, so on. You have to some work to do, but with that you can give the following thing. The first is the following proposition, that what you can prove is that this is a big O of something which is no, it's not a big O. It's first, of course, you have the main term, but the error term is something which you can make explicit. It will be a big O of x over q to the power alpha, let us say, for uniformly for q up to x to the beta. I don't tell you what are alpha and beta, but alpha is less than 1 and beta is positive. For some alpha, not for all, of course, for some alpha, and you can work on that and see. You may write it in different ways, but in any case, you have a good bound for this. So you can do a lot of things with. Oh yes, for integer is completely different. Yeah. And another consequence is that you see now, if you say, okay, I want to look at different functions. I said, you see, I was taking as archetype the function of PIatetski-Shapiro sequence. What can you do? Essentially, you can replace, possible to replace n to the c by smooth function f of n with again polynomial growth. That what you want to say is that all the derivatives are nice up to a certain point. For example, if you look at a Hardy field, if you know what it is, then you take function in a Hardy field. Hardy tried to, you see, well, when you want to say what is the type of growth and you want to have big O of something, then you say it can be x to beta, but it can be x to beta to log times log x to something, or divided by log x, or multiplied by exponential to. So you have a lot of things like that. And so Hardy tried to explain what can be the good terms for this type of things, and those are the Hardy field. This is how we introduce the Hardy field. Okay, so this is the generalization. Of course, we can do better than that, but then it means that we are not going to use this type of demonstration. We are going to use something different, but I cannot tell everything. But at least you see here immediately how you can extend what is said for PIatetski-Shapiro sequences to other type of functions. Okay, just functions for which Vanderkoput will work. Very nice book by Kolesnik and Graham and Kolesnik on Vanderkoput estimates, and so you can see what it is. But I stick to my function, okay, because I would like to say a few other things. So now we have been looking at one residue. So I want to look at blocks of element in the sequence of residues. So 3 will be the complexity of the sequence of residues. Over PIatetski-Shapiro sequence. So I will write UN is something which would be the residue of n to the c modulo q. So in some way, c is given positive, larger than 1, not an integer, and q is a given integer larger than 1. Okay, and I look at the sequence of residue like that. So this is UN. U is UN, is a sequence of numbers, I mean residue, or you can consider the residue I being the integers 0, 1, 2, and so on up to q minus 1. I know purists will disagree with this. I know what I'm saying, but I am saying, however, is a sequence of elements in the finite set. That is important that it is a finite set. 0, 1, q minus 1. What is important is to have a sequence in finite set. So what we are saying is that all the elements occur with the same probability. Now what we can look at is also the blocks of elements in this sequence. Block of element in this sequence, if you take, for example, you take S, let S at least 1. 1 will be just the block of element. And then what you are looking at is you are looking at all the elements, all the sequence UN plus 1 blah, 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 un plus s. So these are elements in your set, S tuple of element in your set. And what you can look at, what can I say about the number of such elements when n varies? I'm looking now at the number of blocks. So what I know is that if S is equal to 1, the number of blocks is equal to Q, because all the elements will occur. I even know that they occur with the same probability, but all elements will occur. Think of square, mod 3. No, there are some which do not occur. Number 2 will not occur. So here we already know that they all occur, and even they all occur with the same probability. We're very happy with that. So this is what we are going to call, maybe I don't invent a new notation, NS of U. This is the number of blocks of length nth, S. What can I say about that? Of course, you know that if you take a priori for any sequence, I forget what I said already, but the number is between 1 and q to the s. Okay, if you take 1, which means that this sequence is constant, now you have sequences which can be full sequences, like we see. So for s is equal to 1. You may have sequences for which you don't have that many. If a sequence is periodic, then the number of blocks you can see is just for all the blocks of length given S is bounded, because then you recover the same one. If it is bounded, you can prove also that it's not completely trivial, that it is periodic. So, and you may have something that tells you that NS of U for some sequences is just S plus 1. These are called Sturman sequences. Okay. So then the question is, for us of interest is to know, for this sequence, if I am interested in this, what is the behavior? I know that for S, I meet everybody. What you would expect is that if it is really a random sequence, you should be in this case. This is a random sequence. Any block will occur, and you may say infinitely many times or just one time. There's no much big difference between that. This is combinatorics, but it's nice. So the question is to know, what can we say about our sequences here? Boom. So the complexity of a sequence of a sequence U will be the lim sup of log NSU divided by the logarithm of q to the s, that is to say s log q. Okay. So this is the complexity, and complexity is between 0 and 1. Okay. And if complexity is 0, U is said to be deterministic if the complexity is 0. That is to say, log of ns of U is little of s. You don't care about the log q at that time. Okay, so now what is Where are we with this sequence? So let us give now something which is not a complexity. We'll think about complexity for SPS sequence for residues. Segal PIatetski-Shapiro sequence. Okay, the first thing is that I must say that all this part is there are some basic things I didn't tell you exactly. I didn't put names because when I say you use Fourier, essentially I gave the name. That is to say, it is what Hermann Weyl and van der Kolk would have done. Then if you have something specific, as we have the value of alpha, the value of beta, then it is attributed to someone. This was basic. This is joint work with Michael Dormota. A lot of people there. Clemens Müllner. In Vienna. Andrei Shubin, who is in Vienna as postdoc right now, and Lukas Spiegelhofer. And myself. Okay. So first result is that if you take S, which is sufficiently small, up to C, then to C, I guess we can do something which is a bit more, which is up to C plus 1. If C is equal to 1 something, you can go to 2, yes. For C between 1 and C plus 1, then you have the following, that NS of U is equal to Q to the S. You have everybody. Not only you have everybody, but time is rushing, so I just say it, I don't write anything, but all the blocks occur with the same probability, with the same frequency. And all block occur with the same frequency. Yeah, which is, if you count up to X, the block will occur with a frequency X divided by Q to the S. X divided by Q to the S. Okay. Now, what is interesting is that there is something which is completely different. It doesn't mean that it is a random sequence. And it is not at all a random sequence. And we start in the first paper to prove that at least we can find, if S is sufficiently large, there's at least one block which does not occur. And we have now improved it to saying that the increase of NS of U is not exponential in S, but is polynomial in S. We have the following, that NS of U is something which is a big O of S to the K for some K, essentially depending on C. So you have a lot of blocks that do not occur. Okay. So it means that the sequence is deterministic. If it is polynomial, it's a little it's exponential, even if you take the log. Okay. So it is deterministic. Now there's something interesting. The conjecture of Sarnak conjecture of Sarnak, 2010, we said the following, that if if a sequence in general, maybe I write it V. If V is deterministic, then, well, there is a function which is very important in number theory, which is, but not only in number theory, in combinatorics and in different other areas, which is the Möbius function. Möbius function is, let us say, if you have a number which is a product of prime, P2 to alpha 2, this is equal to 0 if one of the alpha is at least 2. If you have a number which is not square free, then the Möbius function is 0, and otherwise it is -1 to the alpha 2, no, alpha L, the L, it's -1 to the L otherwise. So it's a nice function if you think of its Dirichlet series. Is Dirichlet series just the inverse of the Riemann function? So this is why it's very important for number theory, because what we are looking for is the zeros of the Riemann. And so when you take the inverse, you know that it will carry all these problems. So this function is a nice one if you sum it, mu of n up to x. This is little o of x, and this is equivalent to the prime number theorem. Okay, and if you know that you have good cancellation, if this big O of x to 1/2, then this is equivalent to Riemann hypothesis. So it's really a good understanding of the distribution of primes. This function, it has very nice property. And what the conjecture of Sarnak is saying is that if V is deterministic, then Vn mu n is O of x. That is to say, if something is too deterministic, you cannot find the prime number by something which is too simple. So even if the easiest case you see as function deterministic takes simply the nu s, the ns of u to be equal to 1 all the time, the simplest sequence you can imagine, then Sarnak conjecture is true. This is already equivalent to the prime number theorem. So it's not completely trivial. Okay. So when you see something which is deterministic, a sequence which is deterministic, you say, haha, can we prove, at least in this case, that Sarnak theorem is true? Okay. And indeed, it's true here. We have also the following, that proposition that summation n up to x of u of n, mu of n, is little of x. But this is not difficult, by the way. Of course, it's something which is as strong. If it is not difficult, it means that you are in the minimal case, that is to say that at least you have prime number theorem. But once you know prime number theorem, it's not much more difficult than that. Okay. So now I just want to say something about the fourth part, but I am conscious that the time is running, but I would like to say one word about it. Yes, maybe I don't tell you the. I prefer to say a bit more on this. I prefer to say something. Why is it so? Yeah. So what you are looking at the value of un plus 1, blah, 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 consecutive value un plus s. Okay. And this means that you are looking at the value n plus 1 to the c, n plus s to the c. Yes, but now this you can expand by Taylor. Forget about the integral part. Integral part will create some difficulty. We'll see later on what it creates as difficulty. But if you look at n plus h to the c, then you just expand it by Taylor. So it is something which is n to the c plus c1. A binomial coefficient, there is no problem to extend, if you take the good definition of it, to extend it for real numerator. Okay? And then you have something which will be h, I prefer to put c minus 1 plus blah, blah, blah. And then you have something which is h to the c minus fractional part of c, c times c, n to the c minus integral part of c, plus something which is, then when you go on with Taylor, you have something which is small, because you have something which is n to something negative, plus a big O of h. This will not be a problem for us. What did I say here? This is not correct. This is c. H to the c plus 1 or c plus 2 or whatever you wish. This is not a real problem. What is important is that the n is negative. Okay. So in some way, your function is not really a polynomial, but it remembers that it is a polynomial. And when you look at that, you say, okay, I know something about the first n's. Maybe the first one are independent, because then it will depend, are those values, mod 1 or mod q, independent? Yes, you can make all this independent mod q. This is fine. And since you can make them independent, this is the first proposition you have. But then it starts to be something a bit squeezed. And then you cannot do exactly what you wish. Of course, something that will be terrible for you is this fractional part, the integral part. The integral part, or the fractional part of the elements you have here, will be something which is somewhat bad. Now, however, if you want to say, I take many elements, I'm thinking of proposition 2. S is large. I take many elements like that. Well, what you are saying is that, maybe I have to say, to put my elements, if you have the first one which are given, you have really a good understanding of those, except modulo 1. But then you say, okay, they are in different sets. And then I want to say what I can say for the other ones. So, and for the other ones, you have to play some games. And just to say it morally how it goes, you have this will be something which is c-dimensional or something like that. But I just tell you in the plane how it goes. You're in the plane, you say, okay, I have some condition, linear condition. My plane is cut into 2 parts. And also another linear condition. Fine. My plane is cut into 4 parts. Then you say, now I have another linear condition. Your planes can be cut into 7 parts, but not 8. And there is something which is not very difficult to prove, that if you cut it k times, then the number of cells you have is something which is polynomial in k. Okay? And the same thing in higher dimension. And so this polynomial comes exactly from that. Your sequence still have in the memory that it is a polynomial sequence, and that you have some constraint in them. Okay? So we don't know exactly what is, we have an explicit value for k. We don't know what is the good value for k. What we don't know neither is it true, for example, do we have, if you take S, which is just integral part of c plus 2, integral part of c plus 2, is it true that you have you may still have everybody, or you are losing someone. Possibly it's possible to have everybody, but then we would like to prove that you have already lost the equidistribution of that. So this is an open question. Okay. And just to finish with an open question, I am not going into part 4, but it is also to look at consecutive elements. You are saying, is it possible to find many blocks of pairwise consecutive elements, not in the sequence of modulus, but in the sequence of the elements NC? If C is between 1 and 2, yes, we can prove it, that you have arbitrarily large sequences of elements which are pairwise coprime. Of course, this is not true with integers. As soon as you take 3 terms, you have 4 terms, you have at least 2 which are even. So it's lost. But you can find arbitrarily large sequences. But we don't know whether this is true for C larger than 2. So maybe I just raised a question. I'm quite certain it is here. So this is the only thing you will retain from part 4. There will be a bit more in the notes of part 4, the conjecture that, is it true? Can one find, let H be given, can one find n, infinitely many n? You see in those questions, usually, finding one or finding infinitely many is about the same thing. Infinitely many n, such that n plus 1 to the c, blah, 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 n plus h to the c are pairwise coprime. No, one can find. Otherwise, it's not a conjecture. It's a question. I give positive answer to that. I mean, I hope there is a positive answer. So this is fine if C is less than 2. We know how to do that. And with Henrik Ivanets, we have, this is a work in progress. We may even count the number of n for which it is true, up to x. Okay. But we have no idea for C larger than 2 to prove something like that. Again, we can do that when C is less than 2 by function, which looks like that, and so on and so on. Okay, it's high time I stop. Sorry for being a bit late. It is very constructive. It is not at all through the through the harmonic analysis. Essentially, what you do is the following. It comes from that, by the way. This is what you have. You have this, and then you have peanut. Okay. So now this peanut, you may really control it and say this is really very small. There's no problem. As soon as n is large enough, this is small because h will be bounded. Little h is up to capital H. Indeed, we can go h up to a constant time log n, but forget about that for the time being. H is fixed. So h is fixed. This is peanut. So now you want them to be coprime. So what you are saying is that you find some nice, oops, sorry, you have some, I don't want to walk on that. This would be a disaster. So you have those two things at your disposal, and H is here, and those two values. So you manage to have those two values, which are that you want them to be always coprime. So this one, you have it to be, maybe you ask that it is divisible by a product of all the small primes. And this one not to be divisible. Or is it that way around? Or the other way around? Because you want them to be coprime. That is to say that when you take So essentially, we'll say the following: n plus h to the c. This you may find out to be very small. This also you may find to be close to something which is what you want. So you want to say that this will be exactly n to the c plus h times n plus 1 c times a times c times n to the c n to the c minus 1. Okay? And now when you are saying I want those two to be coprime, this doesn't play a big role. And then you will have to say that the difference here, it will be divisible by this difference. So this difference, you don't have a good control, but it's not a large number. And what you want is that this number will be coprime with this, and this also will be coprime. And so you are, so it is really constructive and quite easy. No, there is no Fourier business in that. And this is why maybe we don't know how to do with that. Because if you take c larger than 2, then you have another point here. Now what you can say is the same thing, but not for 2 elements to be coprime, but to be 3 elements to be coprime. So if c is between 2 and 3, you can say that they are arbitrarily long, such that if you take any 3 elements, they are coprime. Yeah.